Imaging. I'm Alex Fong. I'm the Vice President of Engineering. Are you seeing my, is that the
I see
presentation
you.
showing?
Now it's perfect. Now it's the presenter mode.
Okay, good. I'm glad I'm perfect. Just talking today about hyperspectral imaging and how it can be used in machine vision applications. So let's talk a little bit about, just as a starter, what the difference is between hyperspectral imaging and conventional machine vision systems. So as we're all aware, conventional machine vision systems, they seek to sort of mimic what the eye does. So they essentially divide up the colors of the world into red, green, and blue. You can make out broad color differences just like the eye can, geometric features, morphology, but you can't get spectral information. Now, with spectrometers, you can get definitely the spectral information, but you can get it for only a point at a time in the entire context of a scene or from a sample. So what hyperspectral imaging does is it combines the capabilities of spectroscopy with conventional machine vision technology approaches, so that you get for every pixel the entire spectra of that pixel. And so you get the spectral characteristics of every point in an image. So what we're doing then is we're able to sense things. We're not just seeing things, but we're able to measure things, like in the case on the right-hand side, this is a potato chip, or as they call it, a crisp in the UK. And we're looking at the coverage of seasoning, which otherwise would not be discernible by eye. So you see seasoning coverage, density, distribution. You can then do categorization by the individual potato chip, by the bag, by the batch. The hyperspectral image kind of looks like one of the moons of Jupiter or something at the bottom, but the orangey bright false color indicates the coverage of a certain type of seasoning, a certain flavor that's on that potato chip. Otherwise wouldn't be detectable, not with your human eye. There are several different types of hyperspectral imaging technologies. I'm not going to go into super detail on this slide, just to say that there's the conventional methods of push broom, band sequential, where the filter moves. A push broom is where there's a grating and you're scanning the spectrum one line at a time. There are pattern filters, much like an RGB filter or RGB overlay on a machine vision color camera, but with more different colors or bands, as we say. Our approach is something called a Fabry-Perot hyperspectral imaging technique. It uses what's called a Fabry-Perot interferometer. It's two mirrors that are moving back and forth with respect to one another. The constructive and destructive interference between the two then sort of dictates which bands transmit through the two mirrors onto the sensor. In a simplest form, you get one band at a time, but we've got an approach that allows you to get multiple bands at a time, and that allows you to have, obviously, faster collection of data, improvement in signal-to-noise ratio, and high resolution and a larger spectral range. We're able to make these little mirrors using a semiconductor process, so it's scalable for very high volumes of production, and they can be designed to operate in the UV visible, near IR, shortwave IR, and beyond. These can be made very compact and robust. You can see a handheld unit there. It's like a pistol grip type of unit that's a contact hyperspectral imager. Others are palm-sized type cameras. They can be put in almost any kind of context or application environment. Costs continues to come down with hyperspectral imaging technology. In the past, these monster type of units, very large, used to be over $50,000 to $100,000. They were made for laboratory use only. They took a long time to collect the data. You needed a PhD to understand what the data meant, because there was so much of it, and it was complicated as spectra, so you need to be a spectroscopist. In the future, we see the costs coming down significantly. We're already fairly close to that. We're less than half the price of $50,000 with our technology, As it stands, we see it going even farther below that. We see it becoming very portable, and we see the results, the output coming in real time. And all of this is because we're getting this great convergence of technological developments happening at the same time. We have, the capability to miniaturize our Fabry-Perot interferometer through semiconductor processes. We have GPUs, advanced graphic processing units, just very high-powered computing that's available at the consumer level, so we can leverage that. We have algorithms being developed, just ubiquitous and in high velocity. So we're able to leverage all of that to create a solution that gives you answers quickly. We can address tons of different applications. We're already working on all of these things that you see up here: product uniformity, ingredient distribution you saw earlier, food freshness. We can see if things are ripe. We can grade them for different attributes in terms of sugar content, in water content. We can also use it for, very importantly, a role in safety. We can detect whether things are leaking, becoming contaminated, foreign objects being included in the product, detection of toxins, pathogens, and inspect the packaging that it comes in to make sure it hasn't been breached. So just a quick sort of demonstration of this working in real time. This is actually a nuclear detector pipe, a nuclear reactor pipe rather, and we're detecting boric acid deposits. This sort of corrosion occurs when there is leakage in a nuclear reactor head, and there's a moderator, which is boric acid, or boron rather, and so forth, boric acid on the surface. And so we're detecting this in about 10 hypercubes per second. Off the surface of the pipe, and you can see it's happening in real time. So we're detecting about 10 hypercubes per second. And so, in summary, hyperspectral imaging provides unprecedented level of detailed product information for assuring quality and safety. Techniques applicable to a wide range of use cases and industries, from agriculture to food production, consumer electronics, and plant inspections. And systems can be configured for an application such that data can be presented in real time. We represent a very cost-effective, adaptable approach to incorporating spectral imaging and machine vision applications. Okay, I think that's it.